Hello everybody, this is Nicolas Zabaras. This is Statistical Computing and Machine Learning, and today's lecture will be on hierarchical Bayesian modeling. So let's see some of the topics the lecture today is going to cover. So we will introduce what is hierarchical Bayesian modeling. So this will be, if you like, an extension of the discussion we had in the last lecture on prior models. So effectively we will introduce a hierarchy of prior models, and we will demonstrate the significance of this methodology through examples. So the first example will be to compute the cancer rates in different cities. And we will introduce what is called the evidence approximation or empirical Bayes. So this will be a method that is relevant to an efficient implementation of hierarchical Bayesian models. And then at the end of the first example, I'm going to give you a review of all the possibilities you have when it comes to hierarchical Bayesian modeling, from effectively starting with maximum likelihood estimation and map estimation all the way to doing full Bayes. And then we will see where in between this evidence approximation fits in. We will do a second example that has a Gaussian likelihood with a Gaussian prior, and we will come up with what is called the Stein estimator. And then we will finish with a last example on predicting baseball scores, that this particular problem will not fit in this paradigm of the Gaussian likelihood, so we will have to do some sort of approximations to make the likelihood look like a Gaussian. So the goals for today's lecture is to understand this very important topic on how to efficiently implement hierarchical Bayesian models with the evidence approximation or empirical Bayes method, and then to learn these shrinkage estimators that are obtained from these methods, and in particularly what's called the Stein estimator. Okay, so if you remember, the whole promise of Bayesian inference is that once you set your prior model and you have a likelihood model, the whole inference process is very mechanical. We know how to compute the posterior of the parameters, we know how to compute the predictive distribution, how to compute the marginal likelihood and do model selection. All of these things by now are standard. Now, however, what we discuss is that a prior is very subjective. So each of us will select a different prior, and obviously, someone may start worrying what is the effect of the priors that each of us introduces in the inference process. So one of the ways to reduce, if you like, the effect of the priors is to use what's called a hierarchical Bayesian method. So let me describe this on a two-level hierarchy. So let's say that you have some likelihood that depends on some parameters theta. So usually what we will do is we will postulate a prior pi of theta. Okay, so let's say you take pi of theta to be a beta distribution that has some parameters A and B. So those parameters A and B, I'm going to call them here phi. So literally I can write my prior as prior of theta given these parameters phi, that they're the parameters A and B in, let's say, my beta prior. Now, in the past, we didn't say anything how we select the hyperparameters. That's how we call these parameters phi. We didn't say much. We said this is A and this is B, and and everybody will select different parameters A and B based on what they think it's appropriate for the particular problem. So in our case, we would like to actually treat phi to start with as random variables. And if we do that, effectively we're going to need a prior pi of phi on the phi parameters themselves. So if theta is are random variables, phi are random variables, effectively a full Bayesian formulation will require that we compute the full posterior of theta and phi, all right, given my data d. Okay? So what we will address today is ways that somehow we will not compute necessarily the full posterior of theta and phi, or maybe we will discuss, if I can put it differently, ways where somehow we can make some approximations on phi that will have less effect on the inference process than if we were to do those approximations directly on theta. And the approximations that I have in mind is to actually use some point estimate for phi, okay, appropriately defined, that somehow we will not be able to use directly on theta, because we have seen that these plug-in approximations, they are not very good in many cases. All right, so in this particular case, if you want to produce the whole posterior of theta and phi given your data, this bold X is my data here, you can actually write this using Bayes' rule as the prior on theta and phi. This is my joint prior times my likelihood. But remember that my data X depend on theta that depends on phi. So if I know theta, I don't need to know what phi is to define my data X. So really, my likelihood is only a function of theta. Okay, so the full joint posterior of theta and phi is written as the likelihood of X given theta times the prior of theta given phi times the prior of phi. So that's my joint prior on theta and phi. And today, the whole idea will be how can we take this hierarchical Bayesian modeling and find some efficient implementation that does not require to compute the full joint posterior of theta and phi, because you can guess that that is going to be a very complicated thing to do. Okay, so this is the simplest possible example that you can think of a two-layer hierarchy, and actually the three examples that we will discuss in the lecture today will involve only these two layers of hierarchies. Okay, so imagine that you have a likelihood that depends on the parameter theta, okay, and the parameters theta depend on, they have some hyperparameters theta 1, and then you put a prior on theta 1 that depends on some hyperparameters theta 2, all the way down to having to put some prior on the parameters theta m. Now, theoretically speaking, you can actually go and integrate all the hyperparameters out, and that way produce if I can say, a robust prior directly on theta, and then use the techniques that we have discussed up to now in the class, but obviously doing some sort of integration like that over the various hyperparameters of the problem will be very expensive. So let's go back to this two-layer hierarchy and see exactly what are the possibilities. So one of them is to produce the joint posterior of theta and theta 1. So before I had phi to be the hyperparameters, I apologize, here I'm using theta 1 for the hyperparameters in the prior of theta. So this is the full posterior, and obviously there is nothing new I can tell you. You can use all the techniques in the course that we covered up to now to compute this posterior. So this will be heavy computation. You have more parameters to deal with. Now, the second possibility would be to produce the conditional posterior of theta. So conditional of posterior of theta on theta 1. And if actually you think about it, many of the things we have done up to now, that's exactly what we're doing. So when, let's say, we put and we say the prior on theta is a beta distribution with parameters A and B, we assume those A and B parameters, and really what we did is we produce the conditional posterior of theta given A and B, and we didn't do anything particular to say what values A and B we will use. So maybe in the lecture today we can address that problem. And of course, the other possibility, similar to what I saw in the equation on the top, will be to produce the marginal posterior, which means, yes, you have to compute this joint posterior of theta and theta 1, but then once you do this, then integrate the parameters theta 1 out. Okay? And certainly, if somehow you can compute this, you can actually use either the conditional or the marginal posterior as you wish. Okay, so so let me define some generic notation, and I know I keep playing with the names of the hyperparameters, but I am going to go back to our notation for the data being this calligraphic D. So my likelihood depends on some parameters theta, and then the prior on theta requires some hyperparameters that I'm going to indicate here as eta. Okay, so you can see actually these errors and the way that I have this equation written here indicates the probabilistic dependencies between d, theta, and eta. But again, I am going to use these probabilistic relations to write down the joint distribution of these variables, but you don't really need to know much about probabilistic graphical models at this point. Okay, so this is we can extend this to multiple levels, right? But I'm going to concentrate mostly on these two-level hierarchies, where my prior on theta has some hyperparameters that are indicated here with this vector of parameters eta. Okay, so let me, rather than philosophizing and trying to be very general, let's discuss a very specific example where we will see exactly how we can avoid having to compute the full posterior of the parameters theta and eta in a two-level hierarchical prior modeling. So this is the example. We assume that we have a number of cities, and we are given the population of every city that I denote here as Ni, and we assume that we know the number of people in each city that have cancer, or as it says here, the number of people maybe that died from cancer. And we assume that xi follows a binomial distribution, where theta I is the rate of dying from cancer, let's say, or having cancer in the city I. Okay? So the objective of the problem is, given Ni and xi for different cities, to compute this cancer rates theta I. Now, obviously, this doesn't look a very difficult problem, because maybe somebody will say, I can go and actually I can compute the maximum likelihood estimator separately for each city. Yes, you can do this. You can actually do full Bayesian inference, and compute the posterior estimates for theta I for every city separately. Or even you can go to another extreme, where take everybody, the whole population in all the cities, and the whole number of dead people from cancer in all cities, and somehow come up with some pool MLE estimate for the whole population. All right? And in many ways, those will be sensible type of calculations to do, but there is a problem, and the problem is, what do you do in a city, for example, that has a very small population, and for that city, let's say xi is equal to 0. So if that is the case, then somehow, let's say your MLE estimate is going to come up to be 0. And that we know it's not a sensible type of estimate. The idea here is, can somehow, for the cities that have very small population, so the cities that they are very poor in data, can we borrow statistical strength from the cities that somehow have a bigger population? And this will be the whole idea on how we can effectively implement this hierarchical Bayes algorithm. So let me go directly to on how we're going to actually tide the cities that have a lot of information to provide for this problem, and the cities that don't have a lot of information. So what we're going to do is, we're going to take this cancer rates theta I for every city, and we are going to say that all of them are tied together because all of them are coming from some beta distribution with hyperparameters A and B, and A and B here are denoted with this vector eta. Okay, so eta is my hyperparameters, and we will see how we're going to compute them today. But the way we're going to link the calculation of the theta i's for every city is by making theta I to come from a distribution that has these parameters A and B. Now, obviously, to be able to use the information from all of the cities, there is the only sensible way to do that will be to compute these parameters A and B somehow by utilizing all the NIs for all the cities and all the XIs for all the cities. So we need to find a way to compute A and B, okay, by utilizing the information provided for every city. And actually, I can tell you right away, we're going to use a point estimate for these parameters A and B because we don't want to implement a full joint posterior for theta and eta. So we're going to compute a point estimate, but that point estimate of A and B will utilize the information from the data-rich cities and also from the cities that are lacking, let's say, in cancer cases, or they have a very small population. All right, so let's look at the equation on the bottom. So the equation on the bottom is literally the anormalized posterior of theta and eta. Remember, if you write the posterior of theta and eta, will be on the top, you're going to have the likelihood times the prior. That's what you see here, divided by a normalizing factor. So this anormalized posterior is basically the likelihood. And for every city, remember, my likelihood is a binomial. Now, the prior is different from each city because each city has its own, cancer rate theta I, but all of them come from a beta distribution that has the same hyperparameter theta, and in generally speaking, we have some prior on eta, okay? And I mentioned we will use a point estimate, but generally speaking, the anormalized posterior for theta and eta will look on the form that you see here. So what I want to do is, before I actually give you the calculation, right, I want to tell you how the results for theta I are going to look like if somehow we compute these hyperparameters A and B by utilizing all the data, okay? And if you're curious, because this is going to take us 2 or 3 slides to see the details, I can tell you that these parameters A and B are going to be fixed by maximizing the marginal likelihood, okay? And when I mean maximizing the marginal likelihood, not just for one city, but for all the cities, okay? This is what is going to give me estimates of A and B that share statistical information from all the cities. So for now, assume that somehow we have, with some smart way, we have computed these parameters eta to a point estimate. So effectively, you can look at this problem as a binomial likelihood with a prior on theta I, but these hyperparameters theta now have been computed by utilizing information from all the cities. So let me go directly to some of how the results will look like, and then we will provide a few more details on how these results are coming about. So what you see on the top is you see the cases with cancer in 20 cities, and you notice many cities don't have any cancer cases. So obviously these are cities with very poor information for estimating the cancer rates. So for example, you're not going to go in city 20 and declare that somehow theta subscript 20, let's say the MLE estimate there is 0. So you're not going to use that estimate and say the cancer rates in city 20 are 0, because obviously in the future you're going to observe some people coming up with cancer. So you need a much more sensible for these cities that appear to have 0 XI. Now also you see that some cities have very high population, some other cities have very small population. So city 15 has a very high population, city 20 has a very small population. So on the third row, you see the maximum likelihood estimation for theta I. So we compute theta I hat separately from each city. And you remember for the binomial distribution, the MLE estimate is basically the counts of xi divided by ni. So that's a very easy way for computing the MLE. And again, the MLE for city 20 is 0 because xi is 0. Now this red line here, you can consider of this as the pool MLE, and I have written it here as all the number of all the people with cancer divided by the population of all the cities summed together. All right, so that's one way to define a pool MLE. And then let me look on what I have on the bottom. On the bottom, I show you the posterior mean of theta I. And remember, theta I follows a prior that is a beta distribution, but those parameters A and B are selected by sharing statistical information from all the cities. Okay, so the hyperparameters have been computed using all the data together. So if you go and you compute the prior mean for theta I, because the beta distribution will be A divided by A plus B, but I denote this as A hat and beta hat to emphasize that these are the point estimates that somehow I'm going to select with some smart method using all my data. And again, I told you that that smart method will be maximizing the marginal likelihood. Okay, so this is my posterior mean for every city. This is my prior mean, and suddenly you can see the posterior mean for city 20, it is not anymore 0. And the reason is because the posterior mean really, it comes up to be a weighted average of the MLE estimate for city 20, that is 0, and of the prior mean that obviously is not 0. So you can see suddenly the posterior mean for city 20 is pulled towards the prior mean that you see this with this horizontal line here. Okay? And of course, I have a similar situation, for example, with city 1 that also has 0 cancer rates. Okay? Now, let me start looking now if somehow you can, you have a binomial likelihood, you have a prior that is a beta distribution, but with a hyperparameter selected in some smart way that we will see shortly. Then you can actually, we already have done this inference problem, right? You can compute the full posterior of the parameters theta I, and if you compute the full posterior, you can actually compute the 95% credible intervals. And let's look at these results. So if you compute the 95% credible interval for city 15, it looks to be a very small interval. Why is that? So let's look at city 15. So you notice city 15 has very high cases of cancer. So X15 is very high, but the population also is very high. So there is sufficient information to actually compute a very good estimate for theta I for city 15 because you have lots of data. So the uncertainty for city 15 in the estimate for theta I is very small. And of course, you can anticipate it that the information that comes from city 15 that has such a big population with so many cancer cases will be helpful for all the cities for estimating the parameters theta for all the cities that basically don't have as big population or as many cancer cases as city 15. Now let's look at city 10. Suddenly the error bars become enormous. So what's going on with city 10? So if you look at city 10, the population is not as high, but there is a reasonable case of cancers in city 10. But if you look at the MLE estimate, the MLE estimate is very high. And and if you remember, the posterior mean is literally a weighted average of the MLE estimate and the prior mean that is computed using information from all the cities. So this MLE estimate that you see for city 10 is obviously in serious disagreement with the prior mean. They are way too far apart from this line that you see on the picture on the bottom. So this disagreement between the MLE and the prior mean is represented here with these huge error bars that you see. So this is how we get this high posterior uncertainty for CT10. And for CT19, if you go and visit the previous slide, you will see that you have exactly the same situation. Okay, so let's now start discussing on how we are going to compute these point estimates for the hyperparameter theta, these parameters A and B that come in our prior model for theta I. So I have written here the very general case where I have the posterior of both eta and theta. Okay, so now we're gonna start doing some approximations, and the approximation we're going to do is effectively we're going to fix this parameter theta with some point estimate. Okay, so we're going to compute eta with some point estimate. And you remember when we were doing a map estimate, a very sensible point estimate to use will be to find the map estimate for the parameters eta. So literally what I have in this equation, I am fixing, so I'm taking the posterior on eta and I'm approximating with delta function that is centered at the map estimate. And the map estimate is P of eta given my data. Now, actually what you see on this integral is not exactly the, the posterior. This looks to me like the marginal likelihood, right? This is the marginal likelihood where theta has been integrated out. So to make this to be the posterior of theta, really the assumption here that I think must be referred to in the next bullet is that my prior is actually the uniform prior. So the prior on eta, for me to write this equation that you see here, is the uniform prior. Okay? Now, if you want to avoid confusion, so we don't really have to bring the map estimate for eta in the picture at this point, and we don't have to talk about the uniform prior on eta, how about if you look at this equation and you interpret this, this is the marginal likelihood, right? This is the marginal likelihood where you treat eta as the parameters in that likelihood. Theta has been integrated out, so when you compute this integral, it is the marginal likelihood as a function of theta, and effectively what you do is you find the point estimate eta that maximizes the marginal likelihood. Okay? And literally, this is what we are going to do in our cancer rates example. And the method that I described where you compute a point estimate of the hyperparameters, it is called the evidence approximation. In statistics, it's also called the Empirical Bayes approximation. And textbooks like Bishop, they call this the type 2 maximum likelihood estimator. Okay? I am going to give you in a little while a summary of all the possibilities, but the easiest maybe way to remember this method is either as the evidence approximation or the Empirical Bayes. So what is the Empirical Bayes? Is fix your hyperparameters to a point estimate where the point estimate is computed by maximizing the marginal likelihood. So this is exactly what we will do in the cancer case, but since I have this general notation here with theta and eta, let me give you, if you like, as a review, all the possibilities that we have seen up to now in this course for a model that has parameters theta and eta. So the first line that you see on the table on the bottom, so this table has been cut and pasted from Kevin Murphy's machine learning book. So what we have seen on the top is computing the maximum likelihood estimator of theta. Okay. Then on the second line, we have the map estimate. So we fix the parameters theta by maximizing the posterior in theta. And you notice in my prior on theta depends on this hyperparameter theta, but usually when we do that, we don't compute eta, we just assign some values to eta. So that's the implication here of the map estimate. So what you heard on the last slide is we compute eta as a point estimate by maximizing the marginal likelihood, and marginal likelihood is literally the denominator that you have in the Bayes rule for the posterior in the parameters theta, okay? And you notice here what you have is the likelihood times the prior in theta with theta integrated out. So when you do this integral, it is a function of theta. Then you maximize it, and that's eta hat, and that's what we call the empirical Bayes or evidence approximation. Now, if you take your marginal likelihood and you also multiply it with a prior on eta, then you actually get a map 2 estimate, okay? So you compute the eta that maximizes the posterior of eta, and to compute this posterior again, inside this marginal likelihood, the parameters theta have been integrated out, okay? This empirical Bayes and map 2 estimate, of course, they are the same if this prior P of theta is a uniform and uniform prior, right? So if this is equal to 1, you basically get the same result. And of course, at the end of the day, you can always compute the full posterior of theta and eta. That will be full Bayes, and that is not very much different from actually the first equation. The only difference is that instead of just having parameters theta, I now have parameters theta and eta. Okay, so we have seen all the ways going from a completely non-Bayesian way to compute the parameters using maximum likelihood to a full Bayesian way using the posterior of theta and eta. So let me go directly to the cancer rate example. And so what we need to discuss is how do we get this marginal likelihood? How do we perform the integration on the hyperparameter theta? So literally, from the equation I had earlier about the joint, the anormalized joint posterior, you can see that the marginal likelihood as a function of the parameters eta, which are A and B, is nothing else but the likelihood times the prior, which is a beta distribution with the parameters integrated out. And I have to do this for every city, right? So I'm assuming here that this marginal likelihoods for every city are independent given the hyperparameters eta. And now you have to compute this integral. You have to compute the marginal likelihood for every city. But I already told you in earlier lectures that this integral can be computed analytically for most of the cases we have seen up to now in the course. And the way you compute it is by using the normalizing factors for the prior, the normalizing factor for the posterior, and then this is the normalizing factor coming from the likelihood. For those who forgot, this equation comes by writing down the posterior in theta I. The posterior will be the likelihood times the prior divided by the marginal likelihood. And then you plug in everything in terms of theta I and the normalizing factors. All the terms that involve theta I are cancelled out, and what you left are basically these ratios of normalizing factors, and that will give you the marginal likelihood. So in our problem, we have an analytical form for computing the marginal likelihood. So what we need to do is we need to optimize this with respect to A and B. It may look a trivial optimization problem because this is sort of a scalar quantity, but these are beta functions. And so you're not going to be able to take the gradient, set them to 0, and compute a direct solution for the point estimates A and B because the equations would be nonlinear, so you need to do some sort of iterations. So if you really want to know how to actually do this type of calculations, a very nice report is by Tom Minka that I link it on the bottom, so you can visit it and see how exactly you can do the optimization of this with respect to A and B. But, you know, again, you may be able to download a black box optimizer that somehow does this for you. We have an analytical equation for the marginal likelihood, and the optimization is something that we assume it's not a big deal. Okay, so if you do the optimization, effectively what you will do is you will produce a posterior where the parameters A and B are fixed to a point estimate. And we have done this posterior before, so I'm not going to start reviewing this problem again. Before we had the case of a likelihood that is binomial and prior that was a beta distribution. This is what we have now. The only difference now here is that the parameters A and B, they are not arbitrary parameters. They have been selected by maximizing the marginal likelihood that you see on the equation on the top. So when we worked on this problem, we if you go back a few lectures ago, you will see that the posterior mean for this binomial beta model, it's a weighted average of the local MLE and the prior mean. And the prior mean, remember, involves it's A divided by A plus B, and A and B are computed utilizing information from all our data from the cities that have very rich information to the cities that have very poor information. So this is empirical Bayes. This is the evidence approximation. Okay, let's keep moving forward and let's do another example. And the example I'm going to do will be one that the likelihood is a Gaussian and the prior is a Gaussian. So this example would be not very much different, and actually we have seen this type of model before, but not in the context of this evidence approximation. So let's assume that we have a number of schools, okay, and I denote the schools here with subscript J, so we have these schools, and in every school we look at a particular class, let's say in machine learning, and in school J there are nj students that take that class. And let's say the grade of a student I in school J is xij. So what we want to find is we want to find the mean grade in the machine learning class for school J. So we want to compute theta j for every school. So again, what's our information is the scores of the students in the classes in the different schools. And using that, we want to compute the mean score for every school. So what I'm going to do is, so we can go directly to the substance of the problem, we're going to link these mean scores in the machine learning class between the different schools. And the way we're going to link them, we're going to put a prior, all right? We're going to put a prior on that, okay? And that prior is going to have parameters mu and tau square, is going to be a Gaussian, and these parameters mu and tau square will be computed using the data from all the schools and all the students. So again, we have a Gaussian likelihood. I maybe forgot to mention this directly, but we have a Gaussian likelihood, so these grades follow a Gaussian likelihood with a mean for the grades theta j for school J, and our objective is to compute theta j, and we're going to link all the theta j's by saying that they are linked because they're coming from a Gaussian prior that has parameters mu and tau square. So let me write down the normalized posterior of theta and d. So this is what you will get in the numerator when you do the Bayes rule for the posterior of theta. Here, the hyperparameters are mu and tau, or mu and tau square if you like. So condition on mu and tau squared, my likelihood will look like this. So I'm going to have a product over all the schools, and then I'm going to have the likelihood for every school, all right? So remember, the grade of every student follows a Gaussian likelihood. So for every school, I'm going to have from 1 to nj, that's the number of students in school J. Theta j is the mean of the grades for school J, so that's what I want to compute. And all the theta j's are linked together between schools because they are sharing the same prior with these hyperparameters mu and tau squared that I'm going to compute using all my data. The only thing I'm going to say here is that we're assuming in this likelihood model that sigma square is constant, and it is the same for all the schools J. You can still be able to handle the case when sigma square is not constant between the schools, but the algebra is going to become simpler, and we don't want to make things to look very complicated in the lecture today. Okay, now I am going to try to bring a little trick that I strongly advise you to actually prove it. So if I can go back, right? So what we have here is for every school we have this product of nj Gaussian likelihoods. Okay, all of them have the same mean theta j and the same variance sigma square. Okay, so xij follows this Gaussian likelihood. Now, you can take this product over all the students in school J and summarize it with one Gaussian, because you can, if you expand this Gaussian, all right, if you expand this and write down the exponent and you sum in the exponent as a result of this product, you can actually show that this product of these univariate Gaussians, they are actually equivalent with the following. They're equivalent with one Gaussian likelihood for one data point that is the sample mean of my xij's. So xj bar is the average grade in the school J. Okay, so I can summarize that product of the univariate likelihoods in school J as this Gaussian for one grade, which is this sample mean, with the same mean theta j as what I had before, but now the variance sigma j square, it is sigma square over n. Actually, more precisely, sigma square over nj, and that's why I put a j there. Literally, you can solve the calculation by taking the product of the univariate Gaussians, expand it in the square term, and then I think you're going to have to simply use an approximation for the sample variance being sigma square, all right, and that's it. Okay. Bottom line, I can summarize that product of the grades over each school as one likelihood term, all right. This is going to make my life very easy, and that likelihood term is having the same mean as before, but the variance now is sigma square over nj, and my one measurement that all the xij's belong is the sample mean. Okay, that's an interesting result, and you can verify it if you want to. Okay, remember now that the hyperparameters mu and tau or eta are going to be fixed to some point estimate that somehow is going to come to maximize my marginal likelihood. So I am already have done this by indicating this as mu hat and tau hat square, and I'm not going to show you in a slide or so on how you compute mu hat and tau hat square, but let's say we did it. We maximize the marginal likelihood. So what we have is, we have now this anormalized posterior of theta given by this wonderful formula. And if you think of this as an anormalized posterior, right, it's a computation we already have done, because this, like, it is one measurement xj bar that comes from a Gaussian with mean theta j, which is our unknown, and then that theta j comes from a prior that is a Gaussian. So you know how to write down the posterior of theta j for this problem, right? So let me, before I do that, let me just say that it's going to turn out that these parameters mu hat and tau hat are going to be computed from these formulas, okay? Don't need to understand yet from where they come. I just put it here to remind you that both mu hat and tau hat utilize all the data. So you can see mu hat corresponds to an averaging of the xj bar over all schools, all right? So you can think of this being the overall mean, and this sigma square plus tau square, it uses a sample variance, all right, that measures these distances of the xj bars from the average mean. Okay? We will derive these equations, and if you can use your imagination a little bit, you may say, wait a second, these equations look like some sample mean and some sample variance of some Gaussian. So maybe it may turn out that the marginal likelihood is actually a Gaussian, and then this estimate mu hat and sigma hat plus tau hat square are really the sample mean and the sample variance from that Gaussian. So if we wait for one slide, we will see that derivation shortly. Okay, so I mentioned we already have computed the posterior for this Gaussian case. So we have, if you hit this link here, it will take you directly on Wikipedia on the formula when your likelihood is a Gaussian. So the unknown is the mean. We have a prior that's a Gaussian. We only have one measurement. Here is where the posterior comes to be. And we can see the posterior mean. It's a weighted average of the MLE estimate in school J and this overall mean grade over all the schools. And BJ is the shrinkage factor is sigma j square divided by sigma j square plus tau hat square. Okay, so this formula doesn't come by a miracle. It comes basically by doing the posterior analysis of a Gaussian with a prior Gaussian for the mean. Okay, so this result we already have used it. Okay. And the only thing that we need to derive is these formulas in blue, okay, that I'm summarizing them again, together with the definition of beta j that comes directly from computing the posterior. Okay. Now, how do we actually compute these estimates mu hat and tau hat square? We're going to have to compute the marginal likelihood, and again, your likelihood here for one measurement, xj bar, was looking just for school J, is a Gaussian, and this prior is Gaussian. So you can actually use formulas for linear Gaussian models, or you can, expand this in theta j and close the square. Whatever way you do it, this is an answer that we already have seen before. It turns out that this marginal likelihood is xj bar with from Gaussian with mean mu and a variance sigma j square plus tau square. And if I put all my these schools together, this is what I get. And now you need to compute mu and tau square as point estimates in a way that maximizes this marginal likelihood. And effectively, what you have is you have this Gaussian, univariate Gaussian likelihood models, and you want to compute the parameters mu and sigma j square plus tau square. So effectively what you can do is you can simply use the sample mean to compute mu, and you can use the sample variance to compute sigma square plus tau square. Now, there is a little bit of complexity that I'm going to try to minimize in this lecture, and the complexity comes that this using maximum likelihood to compute mu and sigma square plus tau square will actually only work if these sigma j squares are the same for all the cities. So we are going to assume that sigma j square, which I remind you was actually sigma square over nj, this is how we derived it before, it is the same for every city. If that is not the case, which, in the normal circumstances, it will not be the case, there are other ways to actually compute point estimates to maximize the marginal likelihood. And for example, you can use expectation maximization. That's a method that hopefully we will have some time before the end of the semester to discuss. All right, so this is how these estimates are being computed, right? if sigma j square is the same, mu hat will be the MLE estimate. So we basically take all our data points, one data point for each school, that's the sample mean of each school, that will give me the overall mean, and then the variance will be the sample variance, and I call this variance here S square. Now, you notice that literally what you need to actually compute, because this sigma square here is known, we only need to compute tau square. So somehow, because you're using data, you need to guarantee that this tau hat square is positive. So it is recommended actually that you use this tau hat square to be the maximum of 0 and S square minus sigma square. All right, that's a sensible thing to do in case somehow your data lead you to a case where tau hat turns out to be negative. So in that case, you will take tau hat squared to be 0. Now, if if you can appreciate this, looking also in relation with the previous example of cancer rates, you realize that we're sharing information about the various schools. This is what makes this point estimate to work, that somehow utilizes information from the data of each cities, and it allows us to do sensible estimations for theta j in, let's say in this particular example, in schools where maybe we have very few students. Now, something that somehow I did not emphasize in this last few slides at all maybe, is that we have a weird situation here. You remember we have this prior on theta j in our example that is a Gaussian, okay? And then that Gaussian had some hyperparameters, and we compute these hyperparameters using the data from all the schools. So effectively, what we're doing is we're doing a crime, right? We're taking a prior, and that prior is being computed using data. So that may look to be against everything we have learned about this Bayesian formalism, but effectively it works, and this is why we call it the empirical Bayes method. It's an effective method, but somehow we have the data to actually control what the priors are going to be about. So let me say a few words about this James Stein estimator, returning back to this posterior for theta j and looking carefully at the posterior mean being a weighted average of the overall mean and the MLE estimate for school j. So this shrinkage beta j is between 0 and 1. So if sigma j is very small, and that effectively means that my information for school j is very reliable, so I have maybe a lot of students. So if sigma j square is very small, then this beta j is very small, so the posterior mean becomes actually the MLE estimate. So the MLE estimate dominates. Now, if there is high uncertainty in school j, and this is sigma j square is high, this becomes 1, and then the overall mean, mu hat, is what dominates. Now, if you take all of these beta j's to actually be the same, you get what is called the James Stein estimator, that I have written it here in the top of the slide in two different ways. So if you see this James Stein estimator, remember that effectively comes from a Gaussian likelihood model and a Gaussian prior, and remember this example with the school grades. This is how this estimator comes about. And again, looking at the posterior mean, it's a weighted average between a sample, a local MLE estimate, and an overall pooled estimate X bar that utilizes information from all the schools. Okay, let me finish the lecture today with the last example that sort of we're going to use this Gaussian likelihood, Gaussian prior example, but the example to start with is not going to fit directly in that model. So let's see exactly what that example is. We're going to look at baseball players, and we're going to take D players and record their scores, their batting scores, if you like, in capital T games. And we're going to assume that the number of hits, Bj, comes from a binomial distribution, okay? And theta j will be the true batting average for every player j, okay? So somehow we would like to use some idea similar to this Stein estimator to compute this average, batting average for theta j for player j, using the previous Gaussian-Gaussian model, but it seems here we have now a binomial model that doesn't seem to fit exactly. So let's see what the issues are, okay? So the MLE estimate for this, the average batting score for player j, I denote here this with theta j hat, is xj, where xj is beta j over t, right? That's my empirical batting average, and that's my MLE, my local MLE estimate. Now, you remember, like in the example that we did for the student grades, all right, we had the Gaussian likelihood, okay, and that Gaussian likelihood, we wanted to compute the mean, and we did that by using information across all the schools, but I remind you that that likelihood we used was a Gaussian, and the variance in that likelihood was independent of theta j. So theta j was the unknown mean that we compute the posterior, but the variance was constant. So let's see if we can come up with a Gaussian model for xj, all right, for xj in this case. So if you, so in other ways, can we actually force xj to follow some Gaussian with some mean theta j and some constant variance sigma square? If we can do this, then we can use exactly the estimator we had before and come up with some shrinkage estimates for the posterior mean of theta j. So can we do this? So if you actually go and compute the expectation of xj, if you take the expectation of xj, that's the expectation of beta j divided by t, and remember the expectation for the binomial is t times theta j. So the expectation of xj will be actually theta j. That's nice. But if you compute the variance of xj, unfortunately, it turns out that the variance of xj using the variance of the binomial distribution is now a function of theta j. So the likelihood model does not fit to what we considered before, where we had xj to depend on Gaussian with a mean theta j and a constant variance, because now the variance is a function of theta j. So it is problematic now on how actually we can integrate information between all the players to compute sensible estimates for theta j for each player. So we are in principle a little bit stuck. So this paper by Efron and Morris many years ago, from 1975, did a nice trick. And he took the xj and he transformed it to a new variable yj in a way that approximately the distribution of yj turns out to be a Gaussian with some mean to be the function f of theta j. You remember my xj, all right, has a mean theta j. So yj has a mean f of theta j, where f of theta j is this complicated function that you see here with arc sign. But notice it comes out that approximately the variance of yj is equal to 1. It's constant. So this is what is called a variance stabilizing transform. And there is a footnote on the slide that tells you how, with a Taylor series expansion, you can come up with this approximation, but it's a wonderful trick. If you map X to Y, Y follows this Gaussian, so you can actually use this Gaussian shrinkage that we discussed before, and you compute a posterior mean estimate, a shrinkage estimate for mu j that I denote here with mu j bar, and then use the equation on the top to go from mu j bar, go from mu j bar, which will be like the y value here, go to a theta j bar. So this is what I have here. I have mu j bar divided by square root of t, sine of that plus 1, and then the whole thing divided by 2. This gives me a shrinkage estimate for the batting average of every player. Okay, so so the shrinkage estimate for mu j is exactly what I discussed before for the Gaussian likelihood, Gaussian prior model for this grades example. So it's exactly the Stein estimator given by this nice expression. So we use this mu j bar and we transform it to theta j bar. Okay, so let me just give you how the results look like. If you compute the MLE estimates for each player separately, this is what you get. When you compute the posterior mean, you get these shrinkage estimates. So these estimates all are being shrunk, as you can see on the bottom of the picture. Let me give you some comparisons of the true values theta j's of every player, and these true values are being computed by using many games using statistical averaging. I'm comparing then the true values with the MLE estimates theta j bar, and also with the posterior shrinkage estimate theta j with a line on the top. So if you look at these comparisons for different players, right, if we can concentrate in any case, you notice that the shrunk Stein estimator, or the Stein estimate if you like, is way closer to the true estimate than the MLE estimate that is computed using information for each player separately. So somehow, by sharing information, this shrunk estimate is in all cases way closer to the true estimate than the MLE for each player. And again, we see a similar situation what we discuss, for example, in the cancer case. You notice in this case, the MLE estimate is overconfident, is very high. So obviously, the shrunk estimate is trying to compensate, okay, using this pool mean, if you like, and that way it comes closer to the true estimate for this particular player 1. Now, since we know the true theta j for each player, if actually you compute the mean square estimate for all the players between the various type of estimates and the true estimates, it turns out that the mean square error where you use the posterior mean is 3 times smaller than using the MLE estimates. So these shrinkage estimates, they do work, they're very sensible, and they provide a very nice way to mix information from cities or schools or baseball players that have lots of data, and use that information for cases where we don't have that much data. So that's more or less this hierarchical Bayes lecture that I wanted to give you, and this implementation that we call the Empirical Bayes or MLE2 formulation, or the name that I prefer is the evidence methodology or the evidence approximation. Okay, and the only thing you need to remember, the hyperparameters are fixed point estimates, and how these point estimates are computed by maximizing the marginal likelihood. That's all for today. Thank you.